we're gonna go over Danksharding. I'm going to be as detailed as I can. Please ask questions, and we'll try and keep it succinct, but I'm not sure that it will be very, very succinct. Danksharding, first of all, is part of Ethereum's. It's one of the changes that Ethereum is bringing in, and I'm not going to describe it in detail simply because that's not the point of this presentation. I will just say that that it's a data structure that we would like to distribute, and we would like to, especially we are worried about availability. So what does that mean? It means that that if I just take say data and I distributed it among players, then my ability to detect if something is missing is very small. Because if I have, say, like I distribute, say, 1,000 bytes, but I actually don't distribute all 1,000, I distribute 999, then a single player that only sees a small subset of that 1,000, it will be very difficult for them to realize that actually I withheld 1 byte. So the main thing here is to worry about availability, okay? Okay, so how do we do this? And remember that in Danksharding, everything is very, very well defined, okay? I'm based on this paper that I wrote, and I'm basically, this is going to be a walk through the paper, okay? So we start with this data structure called DIN, okay? And DIN is simply a matrix, okay, of elements. The width of it, which we call M, is 4,096, right? And the number of rows is N, and that's 256. Okay. Now each element inside this matrix, okay, is a scalar of approximately 256 bits. Okay. And it's actually an element of the scalar field of BLS 12381. Okay. So that's all we need to know, really. Now, this is the raw data, okay? This is essentially something that if we actually have an entity called the builder, okay? The entity builder gets DIN as an input, okay? And it has 3 outputs. One of them is called D. D is an interpolation of DIN, and we will soon dive into the details. The other one is commitments. Okay, and commitments is actually, as we will also see, but it's actually commitments to the rows of DIN. Okay, so if we think of a row of DIN as like a vector of length 4,096, okay, I have 200 and essentially I've got more than 256 commitments, but and I will show why from an information perspective, if I disregard the availability, which is done through redundancy, I actually have 256 commitments in total. Okay, So each commitment commits to a row of D. Now, I'll already say that all the commitments, that the whole scheme is based on KZG, as we shall see. Then the final thing that I produce as a builder are proofs, okay? And actually what the proofs that I produce are actually reveals, okay, within these vectors. And the reveals, I reveal in total, I don't have enough room to write it here, but I reveal this small chunk within the vector that I committed to of length 16. Okay. Now, maybe some other stuff. This
at several points of the segment.
Kylie, it's very hard to hear you. Yeah, maybe write it on Slack, and I will just look on the Slack and answer. Okay. Okay. So each one of these vectors that we commit to is called a blob. I don't know why they chose that funny name, but that's what they call it. And actually, each one of these 16 tuples that they commit to, I don't know, I don't remember if it's got a name, but that they create proofs for. Let's just call it a 16 tuple. Okay. Now we need to actually. No, maybe I'll do it later. Yeah, I'll do it as part of the interpolation scheme. So let's start with the interpolation scheme. So how do I interpolate this data structure D? Okay. First of all, why do I want to interpolate it? So actually, what I'm going to do is I'm going to interpolate it. I'm going to call the interpolated structure D, and then D is going to be 4 times the size of D. Okay, and it's actually made up of 4 matrices that I named D rows, D calls, and D both. We will soon see these names come up. Actually, I think I made a mistake. I think it's actually, yeah, no, this is fine. I think that's how I named them. The original one is D, okay? And then the size that we get with D is actually 4 times. It's 2 in each dimension, so it's 1,900 or 8K, 8,192. And then 512. That's the interpolated or the extended structure. And actually, we extended in this linear way that I'll get into in a sec, but you can think about these extensions as interpolations, and you can already figure out that now that I've got this extended structure, that if I am missing like an element in it, then it's very hard to actually create a situation where I'm actually missing original data. Okay, because even if I withhold as the builder some of this generated structure, I need to withhold a lot to disable regenerating of the original data from the interpolated data. Okay, so I hope that that's clear. I'm not going to go further into it because really I'm more interested in this talk with the construction itself. Now, how do I actually do this extension? So there are, I think, multiple ways. specifically, there are two ways that that are quite straightforward, and I'm going to quickly talk about those two ways, and then we're going to choose just one of them that the Ethereum Foundation selected for Danksharding. So one way to actually create an interpolated structure is if I have some original data, okay, in here, right? Then I can interpolate all the rows of this structure, right? So I create these interpolations, right? I call them interpolations and not extrapolations because they are really like, because it's a polynomial, then it's very well defined, right? Extrapolation problem is not always, the model is not that well defined. So it really is a type of interpolation and not extrapolation. So I can actually interpolate each one of the rows, and I can also interpolate each one of the columns. Okay, the way that I interpolate is by defining a low degree polynomial based on the original data, and then just sampling it outside of the range, and that's actually the interpolated samples. And I can actually also interpolate the interpolated data. Okay, so I can actually go to like now the interpolated rows, okay, on some column, like the last column that I took here, and I can actually interpolate the like the column of interpolated rows, okay? And that's how I get this final piece down here, right? So it's like an interpolation of an interpolation, which is fine. And because, I'm not going to prove it, but because all the interpolations are linear, essentially it doesn't matter now. Like if I want to get to this piece down here, it doesn't matter if I interpolate this column or if I actually interpolate this row from the interpolated values of the columns. The value will be the same for linearity. Okay, I'm not going to prove that now. It's not a hard proof, and actually in the document it's mentioned. So that's one way to do this, and this we call this actually this is like a lot of 1D interpolations. And in the coding world, this is called a product code. Okay. But this isn't the only way. Another way to achieve something very, very similar is actually by doing a 2D interpolation. Okay. Now, a 2D interpolation does the following. It takes this original information pattern. And now you can think that okay. Yes. Kartik, I'm sorry, but I'm not going to get into these details of exactly how the construction, like to justify it, because the point here is just to touch the mechanics of it. And regarding the question, is it revealing several evaluations at the same time? Yes, it's a multi-reveal, and we'll touch that a bit later. Okay. So you can think of this, the product code, what it did is it actually created a polynomial in X. Okay, so like we could do like F row 1 of X. Okay, and that would be like this guy. Okay, so we know that it's a univariate, one-dimensional univariate polynomial. Okay. And then like the next one will be like F row 2. right, of X. Now, what Ethereum chose to do is actually to do something different and to actually define a two-dimensional polynomial, and then like the whole thing is defined as f of x and y. Okay, this dimension is x and this dimension is y. Okay, and then if I define this block as the samples of this polynomial, like evaluations of this polynomial, what I get is I actually get a multivariate polynomial in x and y. Okay. All right. Now, and the degree actually of the polynomial in x is essentially 4096 minus 1, and the degree in y is 256 minus 1. Okay, and I just get a multivariate polynomial in x and y. And that's how Ethereum did it, and whatever, it does create some outcome, but generally speaking, it's very similar. And in the document, we analyze both Ethereum's construction, which is called the 2D construction, and we also analyze the product code construction. But today we are only going to we're only going to touch the 2D construction. Okay. So there's a whole section here of how we actually take these evaluations, right, which we called D-in, and we actually make them into the coefficient version of D-in, which we call C. Okay. Now, the size of C is actually the same size of D-in. Okay. So the size again of C would be 256 by 4096. Okay, that would be the coefficients of this low degree extension. Now, how do we actually achieve this? So this is where maybe I'll say how we can actually achieve this simply, but then I will make a comment. So what I can do is I can say, okay, let's take D-in, and let's say that D-in are evaluations of this polynomial whose coefficients are C, okay, but at certain points. Okay, so we will say, what are the points on which we are evaluated? So the points at which we are evaluated would actually just think about it a sec. So like, right, the first one would be 1 and 1. Okay. The second point that we will be evaluated, it will still be 1 in x, but it will be some omega, and we'll talk about omega in a second. Okay, and then the next one will be 1 and omega squared, and then I'll keep going, and eventually I'll get to 1 and omega to the power of 4095, right? That makes sense. Now I will say that omega to the power of 4096 equals 1. Okay, so omega will be a root of unity. And then I will do the same on the other axis, and I will say that here I will go with, so instead of omega, we'll use mu. Okay, so it's mu and 1 and mu squared and 1. And then I will go all the way to saying that this is mu 255 and 1. And here I will say that mu to the 256 is 1. So it's also a root of unity, but it's another root of unity. It's a smaller root of unity. Okay?
Is mu not just omega to the power 16?
It is. Yes. Yeah. Actually, we will think throughout this thing that we've got another root of unity. By the way, I'm actually misusing omega and mu because my assumption in the document was not this. It was that, and I will soon correct this, was that omega is actually the 8K root of unity, and mu is actually the 512th root of unity. And we actually did it a little bit differently. So we actually, and maybe I'll correct it now. And actually, we looked here at omega squared and omega to the 4, and eventually omega to 8,190. What would it be? Times 2, so it would be 90. Okay. And here we did the same. So this would be 2 and 4 and 255 times 2, so it's 510. Okay. Now, why did we do this? I mean, it's actually, sorry, it's actually the same, right? Like I've done nothing. I basically just took a square root and I squared all the roots of unity. And the reason that we did this is because actually now we would like to extend it, right? If these are the evaluations over this domain, okay? What we do in the extended structure, right, is that we actually, it will look something like this, right? That like 1 would be here, and then 1 omega squared would be here, and mu squared 1 would be here, and here I would have mu squared omega squared, and this keeps going, right? And then what would happen now is that now I have all these new values, okay? And these are the interpolated values, right? And this keeps going, right? So I'm actually like inflating the structure. Now, how do you achieve that? So that is easy to achieve, right? And actually the way to achieve this is via discrete Fourier transform, right? So what we do is we say, okay, let's take D, right? And then we do a Fourier transform. It's a 2-dimensional Fourier transform, right? Because you remember we're actually in a polynomial in XY. So it's a 2-dimensional Fourier transform. We go to C, which are the coefficients, okay? And then let's call it 0 pad, okay? Or actually, maybe I'll do it explicitly. So we have something like this, okay? And then we do the inverse Fourier transform, and we get to D, okay? Now, this isn't exactly what Ethereum did. They did something slightly different. I'll start with the motivation, and then we'll talk briefly about what this means. So if I go back and we look at this, maybe this will be clearer, right? This would be the natural thing that would arise from interpolation. I'd get all these like black squares and get the values there. But Ethereum didn't want that. They wanted a different type of interpolation. They wanted the following. They wanted actually this. They wanted to say no. What I want is I actually want the original data to be here, to be 1, 1, and 1 omega, and 1 omega squared. And that all the way to 1 omega to 4095. It's what I want for the original data. And also I want mu and mu squared, right? And and so I can add lines. And then u to the 255 1, right? And actually, I want this here to be the original data. And I want the interpolation, right, to be this, right? So I don't want this. If you remember previously, we said that the interpolated path is the interleaved path. Okay, so like I space everything out, and then I have all these like interleaved samples in between, right? But they said, no, we actually want you to keep the left corner as the left corner. That's the original data. And the new data, I want extended further, okay? I don't want to interleave. Now, the reason that they did that is because they wanted that each 16 tuple that we spoke about before that is consecutive within this structure to be a coset, okay? And a certain type of coset, okay? You remember that cosets are actually like affine versions of like a subgroup, right? So the subgroup would be like, it would be the root of unity, which here would be, say, if I look, right? Because if I'm looking at cosets like here, right? Like I would look at like a certain like chunk here as a coset, okay? Need colors there. Actually, I think I can. Let me see if I can highlight. Aha, beauty. So if I want this to be the domain of a coset, okay, and I actually want like, where is my pencil? So I want this coset to be the following, and I want this to be, sorry, or I can write it like that, phi 0, the phi to the 1, to phi to the 15, okay? And I just want, and this would be a subgroup, right? Okay. And phi would actually be, I think that's true now.
A subgroup with what operation? A subgroup with what operation?
So I actually want phi to be the 16th root of unity. Okay, so phi to the 16 equals 1. And I just want, and the coset would just be like an offset of that, right? So I would multiply like this whole thing by something, okay? By some, let's say omega to some power I, okay? So I want to have these coset domains available as like consecutive tuples within my structure. Okay. So in order for that to happen, if I do this interleaved version of the interpolation, then I'll have a harder time. I will need to actually reorder the data to get it consecutive. So that's why they wanted to keep it consecutive at first. Okay. Now, to achieve this, using the same discrete Fourier transform or the same technique, it turns out, and again, I'm not going to actually like prove this or get into this right now. I think that you know, whatever, like we can do this offline. But it turns out that if I take the normal discrete Fourier transform problem, and I just do the following. Every time I have within the DFT matrix, I have some power of a root of unity, say omega to the power I, and I actually map it to omega to the power of of the reverse bit order of I. So essentially, I reorder the discrete Fourier transform matrix and do this reverse bit order of the powers. Then I can achieve this type of interpolation, okay? Where I get like my original data to remain consecutive and the extended data to be extended and rather than the interleaved structure, okay? So throughout the presentation today, we are going to assume this implicitly, okay? We're going to talk about DFT, but we're going to remember that it's this it's this reverse bit ordered DFT, okay? And it's a nuance that it's subtle and it actually needs to be handled carefully in the implementation, but we're going to assume that it's fine and leave it out of today's presentation, okay? But it does have implications, not so much on complexity, but more on just the implementation. You need to be careful. You need to always remember that you're like sort of doing these reverse bit ordered things, and that you need to actually be consistent with them in order that the whole thing works, right? You can't do like one time reverse bit ordered and then like another time not reverse bit ordered. Like if I do, say, discrete Fourier transform in a reverse bit ordered style, and then I do the inverse transform in the normal style, then I will get some mishmash of the whole thing. It won't work. So I need to be consistent. Okay, now what we did here actually is I defined in the document, it was very convenient, I defined DFT as simply as matrices. And as you can see, omega, and omega big W is the row DFT because it has the omega as a root of unity. You can see that actually what I did is I didn't use omega to the power 1, but I used omega 1. And omega 1 means that it's the omega to the reverse bit order of 1. Okay, and that's throughout the document. So from now on, we will think of W as the row DFT. Okay, and I've got a normalization here of 1 over square root of n, and that we should just like disregard completely at this point. Now, U is the DFT matrix of the column. And you can see that essentially they are nearly the same, it's just a different size. Okay, but it's important for me to just fix you to this notation because we will be using this throughout. Now, if I go back to how, to what this means with regards to, basically extracting the coefficients, right? So you can see that the coefficient extraction, okay, is done as follows. I'm now thinking of D in the evaluations, right, as the following, as taking the coefficients, right? And then I can do it in 2 ways. If I multiply it, say, by W from the right, okay, then that means that I'm actually, this is like performing FFT, or I'm going to interchangeably use FFT and DFT. performing FFT on the rows. Okay, when I multiply by W from the right, it's essentially like doing FFT on all the rows of C. And then when I multiply with U on the left, it's like performing FFT of all the columns, right? And this is exactly how you get a 2D Fourier transform, right? You take the original structure, C, okay? Now you have a choice. You can do the rows first or the columns first. It doesn't matter because of linearity, but let's just say that I do, oh, sorry, I apologize. Not sure what I did here. I'm just going to, okay. So I can actually do the FFT on the rows first, and I will complete it on all the rows, right? And then and that would be W, right? That's W is the rows. And then I would go and on the structure that this intermediate structure that I created, right? We can call this, I don't know, maybe C prime. I will do the column FFTs. And this is how I get the 2D Fourier transform. And then obviously, if I have D in and I want to get C, then it's easy, right? Because then all I would need to do is actually multiply D in, right, from the left by U to the -1, and on the right by W to the -1, again from linearity. And actually, you can also show that this -1 can be replaced with actually, I don't even need to do this, with the Hermitian transform because it's a DFT matrix, okay? And again, we're not going to go into it, but finally see that this is how I generate the two-dimensional coefficients, okay? And if we want to look at numbers, which we're not going to do so much today, but just a little bit, we're talking about 4,096 FFTs of size, I'm sorry, I'll do it like this. Start with the rows, 256 FFTs of size 4,096, okay? That would be the rows, and then 4,096 FFTs of length 256, okay? And that's actually what I need to generate the coefficients, okay? Now, the coefficients are not primarily what I was interested in, right? I was interested in actually D rows, D calls, and D both, you know, the extended evaluations. And then to get to them, I do the following. So what could I have done? I could have taken C, right? And I could have, say, if I'm now interested in D rows, and I remind you that D rows, right? D is equal to D in D rows, and then whatever, something, okay? So if I'm now just interested in D rows, right? I could have done the following. I could have taken C, 0 pedident, right? And then basically I could have now run the inverse FFT over it, okay? And actually to be completely like consistent, right? we call this the FFT. Actually, let's see. No, the coefficient. Sorry, the coefficient. Actually, the evaluations is equivalent to time. So going from evaluation to coefficient is FFT, and so we call this the FFT. And W on its own would be the IFFT, okay, because it goes from coefficients to evaluation, okay? So to do an IFFT on this thing, right, what I would need to do is actually multiply it by, not by W, but maybe by something, let's call it W prime, okay? Because now actually I need, and W prime is like 4 times the size of W, okay? Because now my rows go from 4K in length, what they were before. In C, they go to 8K in length, okay? And then once I do that, right, then I can multiply it from the left by U because I haven't, I'm only interested now in D rows, okay? So that's one way to do it, but there is a more efficient way, because if you think about it, you've actually regenerated D in again, but maybe you didn't need to regenerate D in, right? But like, right, the result of this would be D in and D rows. But I already have D. I don't really need to regenerate D. I can simply just generate D rows, right? And it turns out that that's possible. Okay, and the way to do it is actually, instead of doing this, you actually keep U and W the same. So you don't go to W prime, and you keep C the same, but you actually need to do something that's called frequency modulation of C. Okay, that's what we call it in signal processing, and it means essentially taking C and doing something that is equivalent to moving it in time shifting it by like half a step. Okay. And again, I'm not going to prove it. It's in the document. It's a simple signal processing operation. Okay, and this omega is actually just a diagonal matrix, right, whose values are actually this frequency shift. Okay, so it would be, in our case, 1 omega squared to omega 4095. Okay, and it's all in the document. So instead of now doing many more FFTs of also a larger size, I stay with the same size FFTs. Okay, and one element-wise product of the matrix C. Okay, so that's how you get, you can see here in the document, that's how you get to D rows, and D columns is also simple. And actually when you do D both, because D both is actually a linear extension in both dimensions, you actually need to essentially do both D rows and both D columns. And you can see now why linearity shows you that you can go with D rows and then do the column extension of D rows, or you can go to D columns and do the row extension of D columns, and you essentially end up with the same. Okay. From implementation perspective, you can see that there is room to save here, right? Because, like, for example, if I already calculated C, this is called omega, right? This shape is lambda. if I already did C lambda W here, right, then I can save it and I can use C lambda W here. So I don't actually need to do this part of the FFT twice, okay, if I'm interested in all. So there's even room to save here in this calculation. And this is all there is to it. So if we go back to where we started from, we can take the, okay, we've done the interpolation. Now we're going to go to the KZG commitment. KZG commitment is actually very, very simple. Okay. Maybe I'll just do it here. We assume that we have a setup, okay, an SRS, a KZG setup. The setup is actually, I think that by now you guys all know the KZG SRS setup. The setup looks like this. Okay, so it's basically just a vector of all the powers of some secret element, and obviously it's like, right, the group element equivalent of these powers, and the length of the SRS, okay, so the length of it, if I can use notation and do it like that, is 4096, okay. How do I commit? I basically want to commit to, and this is something which is a little bit funny because I told you initially that Ethereum decided to go with the 2D approach, right? But once you get to the commitments and also the proofs, we move back to the 1D approach, okay? So when we move back to the 1D approach, we actually don't want to use C. We want to use C rows, okay? C rows is, if you remember, the way that I calculated C, right? I did, it started off by doing FFTs over all the rows. And I said that this was C prime, right? This was equal to C to D W mint, right? So C prime is actually C rows, okay?
Is that like C lambda W?
No, C lambda W is D rows. Now I want C rows. You can think of it as if you look at the original data structure, right, which I've got here, right? You can see it, right? You can see my pointer. Yeah.
No. Oh, okay.
Yeah, the red dot.
Yeah.
So if this is the original data structure, right, then I can ask the question, what are the, if I imagine that each row of D are evaluations of a 1D polynomial, what are the coefficients of this polynomial, right? So, because what we did before is we said, let's imagine that D in is the evaluation on this whole thing, right? On this whole D in, valuation of a 2D polynomial, okay? Of a 2D polynomial. So what are the coefficients of this 2D polynomial? That was C. Mm-hmm. But now we're going back to 1D polynomials just over the rows. So I'm saying that the coefficient of this 1D polynomial, we can call it C rows. And then each row of C rows is the coefficients of the polynomial of that equivalent row. Okay. A bit confusing. So we can say, okay, like for the first one, we'll have, we will say that it's C rows, right? on row number 0, and then everything. Okay, or just do short notation. Okay, so that means like all the sorry, but that's not right. Should be the other way, right? So actually, I want to take no, sorry, that was fine. I want to take all the columns and then just the row 0 and the coefficients of, and these would be the coefficients of row 0, right? And then like row K would be the matrix C rows at K and all the columns, okay? And that would be this. This is some K. So how do I get to this matrix C rows? The matrix C rows is like taking the original data and only doing FFTs, or yeah, FFTs just on the rows. Okay. Now I can use, so now if I want to commit to the first row, right, then I would do essentially like the inner product of, let's call this big S, okay? So I can do something like that, okay? And this is, we know that this would be, from implementation perspective, this is something that we call MSM, okay? So you see that now, if I go to C rows, I can commit to 256 rows. Okay, so I can create like, essentially I can create 256 commitments like that. Okay. But Ethereum want to commit not just to the original rows, they want also commitments to the extrapolated rows. Or sorry, I said I wasn't going to say that. They want to commit to the interpolated rows. Okay. So how do I commit to the interpolated rows? Yes, I can go and calculate the coefficients of the interpolated rows. But instead of that, I can do something a little bit better, okay? Or essentially, I mean, yeah. So it's just, if I go back, I'll show you what I mean. So I can take C rows, right? And I can move to, right, and C rows is now, right, it's for row 0 to 255, okay? Of the big matrix of D, right? If I look at D, right, D is like 512, right, here. So C rows would be the coefficients just of the first ones. Okay. Then what do I do here? So sure, I can go and extend C rows and call it whatever, like C rows 256 to 511. Okay. And I can do that using FFTs, blah, 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 right? But instead, and then I can commit to these. But instead of that, because everything is linear, I can just take the commitments that I built for the first rows and then simply interpolate them for the other rows. And that is much, much, much more efficient. Okay. So how do I do this? So if we call the commitments this nice K, right? We call these commitments, we say that these commitments are right from 0 to 255, Okay, those are the commitments that I got by doing these inner products or these MSMs, right? So you can see actually when you think of the inner product of CI and the SRS, right? So the result of that is actually these Ks, they're actually evaluations, right? Because the setup is like powers of X, right? So these are just evaluations at some secret element S, okay? That's all they are. And since they are evaluations, if I now want to interpolate them, what do I need to do? I need to do an FFT, and then I need to do this frequency modulation, and then an inverse FFT. And this is actually exactly what is being done here on line 32. Okay, you can see that I take the original commitments for the first 256 lines. I do an FFT, so actually U Hermite times those commitments is now something that I can call coefficients, these like secret coefficients. I move them by doing this frequency modulation. That's this lambda, and then I multiply by U, which is an inverse FFT, and I get to, again, evaluations, okay? And this is actually much more efficient than doing another 256 KZG commitments, okay? Even with optimized MSNs. Okay. The last part are the KZG proofs. Please tell me if you guys want, we can actually take a break and then come back and do the KZG proofs if you want to take a break for lunch. Please vote. It's 12:15 now. We can take a break and come back at 1 and continue, because KZG proofs, I think, should take probably a maximum of another hour. They are the complicated part of this. Until now, it was quite simple.
Yeah, so maybe it's not a bad idea.